and just remembering some of those bits. But in short, for now, this is a pointer to a file structure, and it's not clear to us just yet what's actually in that file. I accidentally quit there, so let me go back to structs2.c, and we'll finish this story. So how do you write to this file? Well, if I get as far as here, inside of this if condition, the file opened OK, and I'm good to go to write. So how do I write to a file? It's actually pretty familiar. So you don't use printf, you use fprintf for file printf. The first argument is apparently a pointer to the thing that you want to write to. And what are the second and third arguments, apparently? It's pretty much identical to printf, right? It's the format string. What do you want to write? And what do you want to substitute in for any placeholders? So apparently, I'm going to write integer followed by a new line, a string, new line, string, new line. And I'm going to plug in each of these students' IDs, names, and houses. Then I'm going to close my file with fclose as file close. Then I'm going to go back and free the student's name and house. But one question, I don't free the student's ID number. Why? I don't free ID. It's not a string, it's an int, and we did not allocate that integer with malloc. It was just there inside of the struct, recall. So let's see what the end result here. So this is structs2.c. Let me go ahead and make structs2. OK, it seemed to compile OK. Let me go ahead and run this now. So run structs2, enter student's ID, let's say Matt, Kirkland, student's ID, let's say Rob, Kirkland, student's ID 3, David, Mather. So it still says David is in Mather, but then nothing. But if I do ls now, there's a whole bunch of code from today, as well as this file database. So let me go ahead and run gedit on database, enter. And voila, we've just created this file. Again, so primitive, this format, right? This is not what a Word document looks like inside. But it is our own proprietary file format, just as Bitmap and JPEG have their own file formats. And ours, too, is in just ASCII text, which might not be sufficient if we want to store something like an ID photo. But at least we now have one way of expressing ourselves persistently by writing these things to disk. And it remains then to use these same fundamentals to start linking things together in an interesting way. Let's go ahead and take our 5-minute break now, and then we'll return to that. All right. So we are back. Linked lists are much more exciting when we actually make a mess of them with actual humans. So if we could indulge, are 8 people willing to volunteer on center stage? Have to be comfy on camera. OK, let me decide this randomly. Who's going to come up? OK, here we go. How about you 2, 3, 4, 5, 6. I'm liking this side of the room. 7, 8. Come on up. All right, you lost your chance. All right, come on up. And we are going to hand you the same numbers we see here on the screen. So you'll be number 9. And if you want to go in our usual spot over there, welcome 17. Welcome 22. Welcome 20. Uh-oh. OK, 26. We'll fix the slide to make this consistent with reality. 34. You can be first. You can be pointer. You can be predecessor pointer. Very dramatic. All right. So slight bug. Oh, and this is an image too, isn't it? May I see 20? Who did I get wrong? 29? OK, debugging. One moment, please. Fixed. OK. So that's 26. OK. So here we have a linked list. And let's ignore for the moment how we got to this point already. Let's just assume that we're fast forward 10 minutes mentally, and we already have the ability to create linked lists. And here is the state of our world at this moment. And actually, let's pop out, if you don't mind, pointer and predecessor pointer, if you could be here in the heap for just a moment. So first, this is good. And now this is the point at which we need to really mimic this picture. If you could somewhat awkwardly with your left hand point at the next person. except for 34, where I would point down with your left hand. OK, so now we have implemented a linked list with humans. So what's going on here? So first of all, each of these, oh, you still have to point. Each of these structures has two things inside of the struct. We have an integer, like the number 9, and then we also have a left arm known as next, which is the pointer. So each of these humans represents a struct at this point with those two fields for a total of, little check, how many bytes does each person represent? How many bytes? 8, right? So 4 bytes for the int and 4 bytes for the pointer. So each of these rectangles is 8 bytes on a system like the appliance. Now, first is a little special. So first, what's your name? Lisa is special in that she does not have an integer. She is only a pointer. And so the reason for her being drawn as a smaller rectangle up there is that she's only 4 bytes. But Lisa is super important because without Lisa, we're going to forget completely where this whole linked list is. And without Lisa, we would have a whole huge memory leak if we allocated all of these nodes but didn't remember where the first of those nodes is. So for now, Lisa is special. She's a pointer. And Lisa really is our linked list. So we've had arrays before, and we've had names of arrays, which are really just the addresses, as we've seen. And so Lisa is sort of the equivalent of that. The only piece of data we have to keep around in memory to remember where the entirety of our linked list is the first person, a pointer to the start of the list. And now all of these guys are fundamentally the same. They're in complete structures, except for 34, who apparently is pointing at the ground because that's the end of the list. So that's probably going to represent what when pointing down? So null. We need a special value to say, there's no one else to the left. So when pointing down, this represents storing the null pointer, all zeros in that pointer field. OK, so the first challenge at hand, and we'll make use of you guys. You don't technically have to keep standing there like that. We'll use you in a moment. OK, so let's go ahead and try inserting at the end. So we need the number 55. And actually, let me change it. Let me steal pointer. Can you take on the role of 55? So what's your name?
Lucas.
Lucas. Malloc Lucas. Right? So now we have another 8 bytes inside of which we can put the number 55. And now let's figure out how to insert Lucas into this list. And actually, what's your name again? Joseph. Oh, OK. And I'll take that too. So Joseph, if you want to kind of take charge here and explain just in real human terms, how do we insert 55 into our linked list? If you want to go ahead and make the insertion. Sure. And let me give you this, if this is on, just to explain what it is you're doing here.
OK, so I guess you take him to the beginning of the list, and you know this is where the list starts.
OK.
You go down through each pointer to find the end of the list, and then end up here.
OK, good. So we found the so-called tail of the list. And then what did you do?
Then you insert him there.
OK, so let's push a little harder on what it means to insert into the list. So you put him there, but
so you take the pointer of the last element in the list and put.
OK, excellent. And where should his left hand be pointing?
To the ground.
OK, good. So, and this is actually quite important. Just because you've malloced a node, a structure, put in the number 55, you also have to change what the default next value is. Because just as with local variables, if you just malloc a node and then put 55 there, what's going to be inside of the other 4 bytes called next? It's just some garbage value. And that's really bad in the context of pointers, because if you follow a garbage value as a pointer, you're going to end up in some crazy place in memory, and the odds are that you're going to segfault or core dump. So that was really good. So now we have 55 at the right position. 34 is pointing at 55. Let's now try to do a little something else with this list. Suppose we instead now wanted to insert the number 5. So I need to malloc one more volunteer, please. OK, come on up. Malloc number 5. What's your name? Emmy. OK, so Emmy's been malloced here. We're going to need you again with the mic to handle our insertion at the head of the list and consider now what is fundamentally different about insertion at the head of the list. And the reason, of course, that we're doing head and tail is because we're trying to keep the list sorted, which we've tried to do with arrays in the past. All right? Go ahead.
So now you have her.
Oh, and talk as close as you can.
Okay. So you have her someplace in memory.
OK.
And you want the first person to point to her and her to point to the next person. OK, good. And now even though as humans they did have to kind of shuffle left and right to make room for each other, in memory, because each of these nodes is at some arbitrary location in memory, as determined by malloc, notice what did not have to happen was 19, 17, 22, 26, 34, and 55 did not have to move, right? If they did have to move, the running time of insert would not be constant time. It instead would have been what?
big O of n, right? In the worst case, if we had to move everyone over by one spot in memory, which we would have had to do in an array, it's big O of n. But instead, insertion is big O of 1, constant time, because all we have to do is go right to the start of the list, and we know where Lisa is because she, again, is the special pointer that we always keep around. And even though we had to do a couple things like point her at 5 and 5 at 9, well, that's still 2, 3 steps. It's a finite number. It's constant. So that was a really fast operation. By contrast, what was insertion at the tail of the list?
The same thing?
Well, big O of?
Big O of, well, you had to go through every pointer.
OK, we had to go through every pointer, so big O of n. Exactly, so big O of n. So let's see now what happens if we make this a little trickier. I have one more node, so I need to malloc one last volunteer, number 20. Ansel, come on up. And so we've malloced another node, and take it away. He belongs in the middle. And explain for the audience, if you could, how we find his location, because it's not as simple as the tail or the head this time.
OK, well, in the middle as in?
Well, so in sorted order. So,
sorted order. Okay.
Yes, and you can walk in front if you need to see the actual numbers.
OK, so what's your name?
You weren't expecting it to be this involved, were you, in this demo?
But so you go to first pointer, follow it to the next value, compare the value.
Good.
Then if it's greater than the value in the first element,
OK.
you point to the second one, compare those.
Good. Please just watch where you're walking. OK. OK. And good. And so now how many pointers need to be updated?
Oh, shoot. So however many, whatever element that is.
Good. OK, well, actually, let's do that. Can we pop Ansel out for just a moment? And 17, if you could keep pointing to 22. So just super deliberately now, what needs to be updated in the way of left hands to insert Ansel in the right location?
OK, so he has to point to Hansel.
OK,
he has
good.
to point to her.
Good. Bug. So you just broke our linked list. How and why? And someone else can answer this. I don't want to put you too much on the spot. What was the bug in that? Right, so you have to point Ansel at 22 first, because otherwise what happened? When we updated 17 to point to Ansel, number 20, we now have lost a pointer, namely where did 22 go? Where did 26 go? We have a dangling reference. We've orphaned, frankly, those 4 people there. So this is an example of perfectly memory leak. So well done. So let's fix.
So now you point.
OK, Ansel points to 22, and 17 points to 20, and voila. Whew. OK, so that was a lot of work, but incredibly important now, the order of operations. So let's hold that pause for just a moment, and let's see if we can't round out just a couple of more, because I promise you it's a lot more interesting to look at humans do this than actual C code. So suppose we wanted to remove the tail of the list. Suppose that we said we needed to chop off number 55, or we want to remove the largest element from the list. Where are we going with this? Well, you can imagine now, if we have the ability to represent a dynamic length of a list that's more interesting, more dynamic than an array, we can start to implement that idea of like a stack of trays or a queue in something like a line outside the Apple Store. So suppose the goal now is to remove the highest numbered person, 55. What needs to be updated?
OK, so you can just point her to the ground.
Good.
Free him.
OK, good. But what did, OK, so that's good. But technically, we ran the risk there of doing what again? We technically might have lost 8 bytes of memory because we pointed 34 down, which means, OK, well, where was 55? So we at least need, and I can help out here, we at least need to either invoke me, like a temporary variable, and I point at 55. Now 34 can point again at the ground. And then what do we free? We free this pointer, which is still pointing at the same node. Or what could you also do? Rather than right, you could free 55 first. There's nothing bad about freeing a node that's being pointed at by someone else, so long as you immediately thereafter lower 34's hand. So either you can do it with a temporary variable or just do it in the right order. And lastly, if we want to actually update, say, the head of the list such that it looks like this, we want to remove number 5. Can I put pressure on you one last time to get this one right with no memory leaks? We want to remove 5.
So
what needs to happen?
OK, first, OK, involve the temporary pointer.
OK.
Point at 5.
OK.
And then
Oh, let's talk a little closer to the mic.
OK, point at 5.
Good.
Point her at whatever number that is 9. And then you can free the pointer.
Excellent. So if we could, a big round of applause for these guys. This was not easy. Very nicely done. You guys you can head out to Rob there.